Okay, so for this video, we'll be going through center of gravity. Okay, so please refer to your notes. Now, when gravity acts on a body, every particle of the body is attracted towards Earth. Now, the total weight of the particles can be represented by a single weight acting on a single point. Okay, although every part of the body is pulled down by gravity or attracted by gravitational force, but this total weight of this object can be represented by just a single weight, okay, acting at a single point. So this is what we mean by center of gravity. It is actually defined, so this is a definition, as an imaginary point. It's not really there. It is just somewhere when if you know if it's a regular object, right, then it must be in the center. That's why it's called center of gravity. It's defined as an imaginary point through which its entire weight appears to act. Okay, appears to act, right? Although every part of the object has weight, but there is one single point that if we were able to pinpoint it and support it, it will balance. Okay, so the object can be balanced at its center of gravity because the weight has no moment about the tip of the finger. The perpendicular distance of the line of action of weight to the pivot is 0. Therefore, the moment is 0. Okay. In addition, the finger exerts an equal and upward force which cancels out the downward weight. So the resultant force is 0. In this previous part, the resultant moment is 0. So it will stay in equilibrium. Okay. So let me elaborate more. Okay, this is a uniform rod. Okay. So I would expect, being a uniform shape, the center of gravity is in the center. So if I were to put my finger here as the pivot, okay, as pivot, the line of action of the weight actually passes through the center of gravity. Is there any perpendicular distance? Perpendicular distance is 0. So if perpendicular distance is 0, moments is equals to weight times perpendicular distance, and since perpendicular distance is 0, the moment will be 0. Therefore, it will not be rotating. However, will it be moving up or down? Okay, so if the weight is, let's say, example, if the weight is 20 Newton, how much force do I need to support it? I will need an upward reaction force of 20 Newton. Okay. Now, for regular shape or uniform object, the center of gravity lies at the geometrical center. Okay, so if you look at all this shape, you'll find that the center is roughly where the perpendicular, where the center of gravity is. Okay. Take note that no matter how an object is placed, different orientation, the weight of the object always act vertically downwards through the CG. So in this case, if I use this rectangular box, and if it's a regular object, the center of gravity will be in the center, isn't it? But even if I put it in the upright position, it will still be at the same location within the object. And weight always act vertically downwards. Now, I prop it up on a surface, slanted. The location of the CG is still the same. It doesn't change because there's no other changes to the object. I never mold it into another shape. The weight is still acting vertically downwards. Okay, for non-uniform object, the center of gravity is located nearer to the heavier part of the object. It makes sense, right? Okay, so what if we are given a irregular shape object? How do we find the center of gravity? Okay, so this is an experiment. Sometimes they do test it in O-level to see if you know how to find the CG. Okay, so from this shape that I have over here, it's not easy to see where the where the center of gravity is because it's too irregular. So what do I need to do? I need to punch 3 holes at the 3 corners. The holes to be as far apart as possible, okay. Punch the hole so that the holes are as far apart as possible. Now you need to be able to hang this lamina. Lamina is just a plain flat object. Okay, hang the lamina freely from a support at one hole. That means I may put a pin through this and I hold on to the pin. This thing will then fall with the center of gravity at below this pivot. So let's say I use this point as a pivot. Eventually this thing will swing until the CG is directly vertically below the pivot, the support point. Okay, so we will hang a plumb line. So basically it is your pendulum bob is being weighed down and a string. So with this plumb line we can actually determine how the line looks like. That means the CG is going to be at any point on this line, at any point on this line. Okay, but I need to have another line to see where they intersect so that I know where is the center of gravity. So if I use this first hole to pivot it, to support it, now I move on to using this. Okay, so I go on and then there'll be another line drawn. Then after that I use the third hole to actually pivot and then use the plumb line, draw out the plumb line, and this third line is going to confirm the location that is in this location. The center of gravity is in this location. Okay, read through the steps again and please ask me if you have any question. Okay, next we go to the idea of stability. Stability of an object is a measure of its ability to return to its original position. Okay, so this is a definition. Please memorize. So the stability of an object depends on the position of the CG and the base area of the object. Okay, the lower the CG, the more stable the object is. That's why a F1 Ferrari car, okay, looks very flat. Okay, but the bus, a double-decker, will actually have higher CG. Okay, so the lower the CG, the more stable the object is. Next, the greater the base area, the more stable the object is. So if I have an object that looks like this, and if I tilt it in the other way around, which orientation is it more stable? But before that, where is a CG? For here, because we have more mass, it will be around this place, right? And let's say this is the ground level. Okay, so you can see from here, the base area is very small base area. And because the mass is sort of concentrated in this larger part, so the CG to the ground is actually high CG. Okay, when we say high, it is the location. But if I were to invert it, it will be actually closer to the ground. So the CG is low. And if you were to look at the base area is actually larger. Okay, so to summarize, the lower the CG, the more stable the object is. The greater the base area, the more stable the object is. So we have one more example. Okay, so it shows the number of books arranged in two identical shelves. They are exactly the same, but the books for A is arranged at the middle shelf, for B is arranged at the lower shelf. So this will cause the CG to be at the bottom, nearer. This will cause the CG to be actually higher. Okay, CG is higher, low CG. Over here is high CG. Okay, how about the base area? The base area is actually the same because we are using the same bookshelf. So you can see, as a matter of fact, the higher the CG, the more unstable it is. Okay, let's go through this question. F1, it shows a sheet of metal suspended from a hole in one corner at A. The weight of the metal is 0.10 Newton, so weight is really a force, and the center of gravity is at B. What is center of gravity? Center of gravity. Okay, center of gravity is an imaginary point where all the weight seems to act in. Alright, so this is my CG. I will have the weight coming down originating from the CG, and it's 0.1. Okay. Diagram is drawn full scale. I'm not sure how it is shown on yours. For mine, I can zoom in and out, so there will be some changes. Okay, but for yours, if it's a printed notes, then it should be this fixed scale. Now the sheet turns because of the moment of the weight about point A. That means about point A means point A is the pivot. Okay, so it turns because of the moment of the weight about point A. We'll find the moment later, but they want us to state what is meant by moment of a force. Okay, so this is the definition of the moment of a force. It's defined as a product of the force and the perpendicular distance of the line of action of the force to the pivot. So this is another definition that you need to memorize. So for part 2, using a measurement taken from figure 1, calculate the moment. So how do we calculate moment? What's the formula? Moment equals to force times perpendicular distance. Of what force? Of the weight about point A. And we already say that point A is the pivot. So on figure 1, indicate the measurement that you make. Since A is the pivot, I'm going to measure the perpendicular distance of the line of action of the weight to the pivot. So still remember, in order to find the perpendicular distance, I always need to extend the force to show the line of action of the force. Then this will be the perpendicular distance. So this is a part that you should be measuring. Okay, so once we have this perpendicular distance, we can multiply by the weight and we'll get a certain value. And of course mine, because it's zoom in and out, I will not have the same value. But I will take 0.1 times the perpendicular distance, measured perpendicular distance. Okay. Now the sheet in figure 1 will swing freely and come to rest. Why? Because if there is a moment and the moment is actually clockwise, it will swing. It will swing in a direction of clockwise. Okay, and swing freely. Of course, when it swings, it will not come to a stop immediately. It will eventually come to a stop. It will not come to a stop immediately. Okay, so in the space below, sketch a diagram of the sheet in its final rest position. Mark point A and B on your diagram. Okay, so this is a sketch, right? A is still the pivot, just that I changed the orientation a little bit. So this is A. It's still the pivot because it's still hung by there. But why is this the final rest position? It will swing freely until, remember, this part B is actually the CG. So how do we draw the weight? The weight is always drawn vertically downwards, right? So I have my weight of 0.10 Newton. There's still no change, right? The center of gravity is still at B, but it will swing until this position, because when I draw the line of action of the force of the weight, we find that this line of action actually passes through the pivot. Passes through pivot. If it passes through pivot, the perpendicular distance is 0. So the weight multiplied by perpendicular distance will be 0. So the first point is the line of action of weight of W passes through the pivot. Okay, so the perpendicular distance from the line of action of the weight to the pivot is 0. And since moment equals to force times perpendicular distance, the moment is 0. Okay, the moment is 0. So this is explaining part 2. Okay, explain why the ship remains at rest in this position. The CG, the laminar actually swings until the line of action of the weight passes through the pivot. Okay, the perpendicular distance is 0. So since force times perpendicular distance is 0, the moment is 0. So there will be no more turning effect. Okay, now the metal sheet is now placed on a table, flat on a table. State 2 reasons why it's more stable when it's placed flat, when it's placed on a table in a vertical position. Right, when something is lying down, it is more stable because CG is lower. Alright, let's see if I put it vertically versus on a table versus now it's being flat on the table. So the CG is lower. Alright, and if you were to look, the contact area is just this small strip over here. But now because I'm lying it flat, okay, the base area is larger. Okay, so this comes from the idea of stability. The lower the CG, the more stable it is. The larger the base area, the more stable it is. Okay, so this is actually a summary. So you need to know center of gravity, the definition. Stability is actually affected by lowering the center of gravity and increasing the base area. Moment of a force is actually sometimes called torque. It can either be clockwise or anti-clockwise using my pen trick. Okay, if you are not able to visualize, you better learn the pen trick. Okay, it can be found in this formula. Moment equals to force times perpendicular distance from the line pivot to the line of action of the force. In addition, you need to know the 6 steps of solving. Okay, so principle of moment is sum of clockwise about pivot equals to sum of anti-clockwise moment about a pivot. Okay, so when will this thing be in equilibrium? When the resultant force is 0, F net equals to 0. Acting on the object, F net is 0. The resultant moment is 0. Net moment is also 0. Alright.